This is an introduction to a technique called inductively coupled plasma optical emission spectrometry. We refer to this technique as ICP-OES. In this slide, what we could appreciate is one of the hearts of this technique, which is the ICP torch, that is illustrated by a very hot plasma, about 10,000 degrees Kelvin, that is able to analyze and atomize almost all the elements that are present in any sample. Two key characteristics of ICP-OES will be the ability to introduce these elements into the atomic state and then obtain emission spectra from these elements. Analytically speaking, these elements include almost all the elements of the periodic table, with the exceptions of the noble gases, some of the low atomic weight elements, and some of the internal transition elements that we have over here. So in general, what we would like to do then is understand a little bit more about the fundamentals that are behind the use of this particular technique. And we will start by looking at the energy diagram of an element, for example, magnesium. So what we have here is a plot of energy versus different electronic states of the magnesium atom. What we can see here is some quantum numbers like 3, 4, 5, 6, and 7. We also can see another quantum number that is represented by S, P, D, or F. Now, if we look at this energy level diagram, we can see that some of these correspond to the ground state, the lowest energy possible, and some of them correspond to excited states, and some of them even correspond to ionization states. In order to understand emission of light or emission of light from an element, we will focus first on excited states, and then we will appreciate that when there is emission of light, there is going to be a transition from one excited state, for example 4D, to one that has less energy, such as 3P in this particular example. We notice as well that these transitions are illustrated by a diagonal or a line. The thicker the line, the most probable that transition will occur. We have here as well a number, 5528. This corresponds to the wavelength of light that is emitted when this transition occurs. Another way to illustrate these transitions is by looking at an emission spectrum. Here we have a representation of the same line that we saw before, and as we can see on the upper part of this slide, we have several lines indicating that for each element there is going to be multiple transitions that will lead to multiple wavelengths of light being emitted. We can see that 5528 angstroms is very intense, and there are some others that are less intense. If we really would like to appreciate the complexity of these systems, we can even go to, we can plot these intensities in a log scale, and we can appreciate that for each element we have multiple, many different lines that are part of this particular emission system. Another way to represent each one of these lines is by trying to blow up what happens in terms of wavelength. We have here a nominal wavelength for magnesium, 5528 angstroms. If we look at exactly what this represents, it represents a line profile. Each line that we observe in a spectrum has a line profile. That is, we can plot the intensity or the relative intensity of light versus wavelength. Here's an example of a line profile in which the nominal wavelengths that we observed before for magnesium could be represented by lambda naught. At that point, we have a given intensity P. This is the intensity is an important property because it allows us to quantify the abundance of an element. The second component of the line profile is the width, usually represented as the width of the profile at half maximum, that is at p halves, and is represented by delta lambda 1/2. Now, it is important to consider what causes the width of these profiles. The first cause of that is the uncertainty principle, just natural broadening. It's a fundamental limitation of nature. So even the thinnest lines possible will have a very thin, will have some width. The second component that contributes to broadening or a line profile is Doppler broadening. This results because in all the collection of atoms that are causing this emission, there are different velocities resulting from the high temperatures that we have in the system provided by the ICP torch. Now, this is going to cause an additional broadening that is known as Doppler broadening. The third component is pressure broadening, usually done because most of this emission happens at atmospheric pressure, and indeed, if the pressure was even higher, the broadening would be even more. Now that we have said that, it's important to understand a little bit more of the process that will lead to ICP-OES. And for that, I will be drawing on the board a description of what happens in this particular case. The instrumentation that is used for ICP-OES will consist initially of a sample reservoir, usually in solution, a way to bring that sample into the gas phase through a nebulizer, a way to take the aerosol droplets into the ICP torch that, as we saw in the initial slide, provides extremely high temperatures. And at the same time, in that torch, we're going to have atomization, that reduces all the components in the sample to their atomic state. And when the atoms are produced, the same high temperature will provide excitation, and that will lead to emission of light. Because we have multiple elements and we appreciate the complexity of the spectrum of each element, it is important to do a selection of the lambdas of interest. And that selection leads then to the measurement of light that has been emitted. It is the combination of these components that we will be discussing next. Now that we have described in general the several components of an ICP-OES measurement, let's analyze one component at a time. The first component is the ICP torch. The ICP torch is usually a set of concentric tubes made of quartz, a transparent material, in which the sample is introduced in an aerosol form that we described before, and this aerosol is carried by argon. When the sample reaches, or the aerosol reaches this region, this is exposed to the ICP torch. Now let's talk about the origin of the plasma resulting in the ICP torch. The plasma results from the presence of an electromagnetic field provided by a coil that basically surrounds this region. This coil is subjected to a very high frequency and very high current electromagnetic field, which results in the production of a magnetic field, and anything that is ionized in the process, in the ions that are present in this region, will then be moved due to the presence of the electric field. It is the rapid movement of ions that will basically cause friction and will lead to very high temperatures that are characteristics of the ICP torch. One of the basic principles of the ICP torch is the chemical reaction that leads to the formation of argon ions. This reaction consists of argon in the gas phase and, provided by the high temperature and additional energy, will result in the production of an argon ion plus an electron. This basic reaction is the one that will lead to the formation of plasma. Now that we understand that the basic reaction of this is the production of argon ions, it's important to understand how the temperatures, the result, are distributed in the ICP torch. The ICP torch usually has different regions of different temperature. The hottest region is right at the point where the plasma is emitted. Plasma is going to be a combination of argon ions, electrons, and photons. And as we can see, as we move away from this region, we observe lower and lower temperatures. We also see changes in the plasma that is important to describe from the point of view of its photon composition. The photons that are produced in the plasma could be of three types. One, they could be photons resulting from the ion, electron recombination. They provide a continuum spectrum. Hence, one can imagine that the white appearance of the plasma is due to this continuum spectrum. There is also present argon and argon ion lines, that is, emission lines. And finally, there is another phenomenon called the Bremsstrahlung effect that results from having ions going from high velocity to a velocity close to zero. So the optical components or the photons that are present in a plasma then will be the ones that will result from this and will contribute to the background that we observe in the analytical signal. There are two possible configurations to do an analytical measurement by ICP-OES. The first one is the axial configuration. This configuration provides high sensitivity because it allows us to collect many photons from the element of interest. The second configuration is the radial configuration. This configuration is good when one is interested in obtaining high selectivity, because we can control easily the region from where photons are collected. Hence, we are able to eliminate the plasma photons. Another key component to understand how ICP-OES works is the collection of emitted light. As we see here, we have a representation of the ICP torch, and ultimately all the light that is emitted is going to be directed through an optical system. The main features to illustrate here are those related to the ability to separate different wavelengths of light. This is accomplished by using a grating and a prism, and they have the ability to disperse the light in perpendicular orientations. The net result of that is that when this light is imaged onto a plane, represented here by this particular drawing, each wavelength will have a unique position. It is the ability to recognize that unique position that allows us to monitor the emission of each element separately. That said, it is important then if we would like to analyze several elements and if we know the wavelength of emission of each element, we are able to simultaneously analyze all of these elements. Here's an example of a typical calibration curve that demonstrates the ability to analyze beryllium, chromium, cadmium, zinc, and lead in the same sample, in the same measurement. It's also important to appreciate that in this particular plot, we have intensity ratio versus concentration of the analyte. This representation as a ratio is because we are using also an internal standard, yttrium, that has a characteristic wavelength of emission as well, and we are comparing the intensities of each element with respect to the intensity of this particular element used as an internal standard. The third component or feature of this plot is that we have added to the sample several potential interference. Tap water that has a collection of multiple ions, calcium plus magnesium, and sodium. And as we can see in the plot that we have here, when these are present, illustrated by the circles, the triangles, and the squares, there is no deviation or interference due to the presence of these interferences. That is, this technique could be quite robust for the analysis of several elements, even when some interferent components might be present in the sample. For more information on this technique, see the textbook Skog, Holler, and Crouch, Principles of Instrumental Analysis, 6th edition.